We'll look now at a chain of masses all connected together by a piece of string. And we'll look at these masses, these blue circles of mass m, moving up and down purely in the vertical direction. Now, we could have done a derivation similar to this for masses moving longitudinally, connected by springs with spring constant k. And in fact, once we have the results up here for the transverse motion, we can make substitutions to get the result we would have had for this derivation here. So we don't need to do both of them really. We'll just look at this one over here. So moving onwards, we'll derive an equation of motion first for this mass in the center here. So the force on this mass is given by mass times acceleration, yr double dot. Now the forces on this mass come from the tension in this string. So we've got some tension T, and the vertical component of this tension is going to give us the acceleration in the vertical direction. So the tension is T is the tension in the string, times sine theta 1 on one side and sine theta 2 on the other side, and it's in the negative direction, so the force is opposite to the direction of displacement. Now, we can re-express sine theta 1 and sine theta 2 in terms of the opposite divided by the hypotenuse. So we just use geometry to re-express sine theta 1 and sine theta 2 in terms of these triangles here. Now we recognize that the distance b is much greater than the difference in height between the masses. So we're thinking about small oscillations compared to the distance between the masses. And this allows us to eliminate the difference in heights here. So we can rewrite this equation here as being approximately equal to, in this regime, taking out a factor of the tension, still we've got the difference in height divided by b here, and another difference in height divided by b, taking out a factor of b. We have tension divided by b multiplied by this combination of heights, yr minus 1, yr, and yr plus 1. So that gives us this equation here, that mass times acceleration of r, y double dot r, is equal to all of this. So this works for every mass in this chain, with the exception of the first mass and the last mass, because they'll be connected to some sort of fixed restraint. So we can combine that with equations for the mass all the way over on the left hand side here, where there's no yr minus 1, so we just get negative 2y1 plus y2. And similarly, the last mass in the chain will be connected to some fixed point over here, and so yr plus 1 goes away. So we have equations for all the masses in the middle plus the masses on the left hand side and the far right hand side. Now we can take these equations down here and express them in matrix form like this. So on one side we have a vector of the accelerations of y, and here we have a large matrix with a factor out the front, and the matrix just has 1s on the off diagonals and negative 2s down the main diagonal, and it's multiplying this vector of just pure y on the right hand side. As this matrix equation, we can use the techniques we had for a pair of coupled oscillators and go ahead and find the frequencies of the normal modes, and indeed the patterns of the normal modes as well. Now, we did this derivation for the transverse motion of these masses. If we'd done the derivation for masses being pulled in the longitudinal direction by springs k, then we get exactly the same equation, except that t divided by mb, this factor out the front here, would change to k on m, and the y's would change to x's. Other than that, we get exactly the same equation for the frequencies and normal modes. So to have a look and see how these normal modes and frequencies behave, we're going to look at a simulation which is handily provided by this website here. So here's a simulation on that website. We can choose whether to simulate horizontal motion or vertical motion. Let's have a look at the horizontal motion first. So we can displace a mass and then start the simulation and look at the motion. We can also, instead of initially displacing a mass in a particular direction, we can start with a particular normal mode. So here's the symmetric normal mode. I can turn the symmetric normal mode off and turn the anti-symmetric normal mode on. Or we can look at superpositions of the symmetric and anti-symmetric modes, and with different phases. So that's the horizontal solution. Exactly the same for the transverse solution. Here's the symmetric normal mode, the anti-symmetric normal mode, and combinations of the two. You'll note that if we start with some initial displacement like this, then this indicator bar down here shows you that the superposition of normal modes and the phases of the normal modes required to get this initial condition, and then when you start, the normal modes just evolve at the speeds, the frequencies determined by finding the solutions to the eigenvalue equation. So that's 2 masses, we've seen that before. Now we can increase the number of masses. So let's go to, 6. So again, we can do this trick, we can displace a single mass. This shows us the superposition of normal modes. We can start simulation, and now we see how the situation evolves. We can stop, zero the masses, and look at the normal modes on their own. So that's the first normal mode, the lowest frequency, like that. The next normal mode looks like this. Fifth normal mode looks like this. And the last normal mode is always the adjacent masses moving in antiphase. So that's how it works for 6 masses. The maximum we can do is 10. And what you'll notice in this case, if we displace one mass at the end here and then start the simulation, this starts to look a lot like a wave propagating from one end to the other. And this is actually what we anticipate, is that as we increase the number of masses and reduce the distances between them, the situation will sort of transfer from being one where we have discrete masses into some sort of continuum situation. And so this is what we'll do next. We'll reduce the size of the mass and reduce the distance between them till they're infinitesimally small, and this way derive a wave equation.